Lecture 3 on vectors. A vector is essentially an arrow. It has two main properties. The first property is the length of the arrow. This feature here represents the magnitude. It's a scalar, or a number. From the head of the arrow, where it points, represents the direction of that magnitude. The magnitude could be the amount of speed, the amount of acceleration, the amount of force, and the direction of that speed, acceleration, or force. Let's look at this example here. We have that Jenny runs 3 miles to the east, then 4 miles north. Find the angle and amount of her net displacement. So we draw our vectors here. She runs 3 miles east, 4 miles north. 3 miles is the amount, the magnitude of the displacement, and the direction to the east. Then 4 miles is the amount of displacement to the north. So we draw that vector perpendicular. East is perpendicular to north. So our net displacement we're calling D here. Find the net displacement D. And then we connect our arrows. As you've already seen in the lecture, and you have done from your reading, we start our vector addition from the first vector added, the 3-mile vector, the second vector that's going to be added, the 4-mile vector, the tail, this spot right here, the tail of the 4-mile vector is added to the head of the 3-mile vector. And our net vector, our net displacement, that vector D starts at the tail of the first vector, the 3-mile vector, and goes out to the head of the last vector, the 4-mile vector. So go from the beginning of the 3-mile vector to the end of the 4-mile vector, as you've already seen from the lectures. So we add 3 miles plus 4 miles perpendicularly. The vector addition gives us the displacement vector. It's the hypotenuse of a right triangle. Pythagoras' theorem tells us 3 squared plus 4 squared equals 5 squared, so the displacement is simply 5 miles. What's the angle of this displacement? Well, opposite over radiation is tangent theta, 4 over 3. Inverse of that gives us the angle. So we know the displacement is 5. The inverse of tangent of 4 over 3 is approximately 50 degrees. Significant figures, we have 3 and 4 and 5, so roughly 50 degrees is the angle of the displacement from the horizontal. Next problem, Johnny runs 1 kilometer to the west, then 1 kilometer south. Find Johnny's net displacement. 1 kilometer to the west, 1 kilometer to the south. The displacement, again, by head-to-tail method, is the hypotenuse of a right triangle from the vectors pointing west and south. We do Pythagoras' theorem. 1 squared plus 1 squared equals d squared, so therefore the displacement is root 2. So root 2 kilometers is the displacement. Again, inverse tangent of 1 over 1 is 45 degrees. Equal sides of the right-sided triangle obviously means the angle has to be 45 degrees. Let's go back and review our basic vector addition. Vector A plus vector B by this head-to-tail method. A plus B equals C. So C's tail starts at the first vector to be added, the tail of A, and ends at the head of vector B. I use a double arrow to represent the net vector. A plus B plus C equals D. Notice this is different. A plus B plus C, I have 3 vectors that are being added. Again, the net displacement vector starts at the first guy's tail, A, goes out to the last guy's head, the head of vector C. I can use Pythagoras' theorem, A squared plus B squared is equal to C squared, to show A plus B plus C in vector form. That would be my scalar addition, A squared plus B squared equals C squared. A plus B plus C in vector form gives us this. Now, A minus B equals C. Let's do vector subtraction, the addition of a negative vector. Vector A plus the negative vector B. Negative vector B is the same as positive vector B in magnitude, but opposite in direction. B points down, negative B is the same length pointing up. So A plus negative B, or A minus B, equals a new vector, not C, but D. So we see A plus vector B plus vector equals vector C. vector A plus the negative of vector B, or A minus B, is equal to a different vector D. Notice C vector and D vector aren't the same vector. They point in different directions. We can still use Pythagoras' theorem. A squared plus B squared is equal to D squared. The sides of the right triangle equal the hypotenuse. A squared plus B squared equals D squared. Let's look at one of those lecture questions. Which of the vectors represented here, we have vector P and Q. We want to do the addition of vector P plus vector Q. Which of the choices A, B, and C will show us the addition of P plus Q? Well, I take vector Q, I slide it around. I take vector Q and slide it up to the head of vector P. The tail of Q has been slid up to the head of vector P. As long as Q, the vector, is the same length and same direction, it's still the same vector Q. First guy's tail, vector P's tail, out to the last guy's head, vector Q. Gives us the resulting vector. From A, B, and C, and D, you can choose the right one. But I could have said Q plus P. As we've seen from the lecture, you know that P plus Q is the same thing as Q plus P. The order doesn't matter. Showing Q plus P being added or P plus Q being added by the head-to-tail method gives us the same resultant vector. And hence we can find the correct choice between A through D. Vector Q, the opposite of vector Q, is negative Q. So what is P plus minus Q? It's the same thing as P minus Q. So to show P minus Q, we take Q, flip it around the opposite direction to show it's minus Q. And so we do the head-to-tail method, P plus negative Q. So I take Q, negative Q, put its tail at the top of P, and my resultant vector starts from the first guy's tail of P out to the last guy's head of negative Q. And I get the vector, the net vector, with a double arrow drawn. And from this we can choose the correct choice below. I can go the other direction. Negative Q plus P gives me the resultant vector that I'm looking for here, and it gives me the same vector. I see negative Q plus P gives me the same vector as P minus Q. So negative Q plus P is equal to Q minus P. Sorry, negative Q plus P is equal to P minus Q. Again, this is the same thing as you learned in lecture. So P minus Q is equal to Q plus P. All right, now let's look at this one here. So what I'm doing here is I want to take, as you've already read this slide from the lecture, and this is one of your lecture questions, we have here labeled vectors P, Q, S, and R. I want to take these vectors and express them in components on this incline. So I took the vector P, the vertical upright vector P, and broke it into components. I'm calling the components P perpendicular and P parallel. So P parallel is by definition perpendicular to the other component. The component's always perpendicular, as you know. And I took the vector P, I made it the hypotenuse of the right triangle with the sides are P parallel and P perpendicular. So P perpendicular means it's perpendicular to the incline. P parallel means it's parallel to the incline. So I followed the instructions in this question to take this vector and express it into vector P and express it into components parallel and perpendicular to the incline. I could have put parallel P and P perpendicular parallel to the incline and perpendicular from the incline and expressed it this way, and I get exactly the same result. Still the same parallelogram. Doesn't matter where I put parallel P and perpendicular P. I just express it for convenience. Now let's look at vector Q. Vector Q, I want to break it into its components. Components of Q parallel to the incline and Q perpendicular. Make Q the hypotenuse of a right triangle. So here I have Q parallel and Q perpendicular. Now, Q parallel, Q perpendicular are the sides of the right triangle where Q has been broken up as the hypotenuse of this right triangle into its components. Now, using the given numbers, the angle, let's say, is 30 degrees, so sine 30 degrees, as we know, is opposite over hypotenuse, so Q perpendicular over Q. So Q sine 30 is equal to Q perpendicular. Using the numbers here, we've got, back up here. Using the numbers here, we're told that each one of these vectors has a length of 4 units. Labeled vectors have a length of 4 units right there. So Q is a length of 4. Sine of 30 degrees. Again, how do I know this is 30 degrees? Because my incline is 30 degrees. So that angle of Q to Q parallel must also be 30 degrees. I know this because this angle 30 degrees and this angle right here must be the same. And I can compute that by seeing that if I take a vertical right down here, I know this angle plus the angle between Q and parallel has to add up to 90 degrees. So if this is 30 degrees, where I circled over here, then this guy must be 60, and 60 plus 30 again gives me 90 degrees. So I know it's Q sine 30 is equal to Q perpendicular. So 4 is the value of Q, as we're told from the instructions. Sine of 30 degrees, as you memorized, and you've seen from the previous problem videos, is 1/2. So Q perpendicular is a length of 2. Q cosine 30 degrees is equal to Q parallel. Again, 4 times cosine of 30 degrees can give us the value of Q parallel. Now let's look at R and break R into its components parallel and perpendicular. Again, that's 60 degrees. I can see 30, 60, so that must be 30 degrees there. This tells me R parallel is equal to R sine theta 30. R parallel being opposite the 30-degree angle. I'll use the 30-degree angle because I already know that the incline is 30 degrees, the one that's easy to measure from the horizontal. So R parallel in our triangle of components is opposite 30 degrees. So R parallel is the component opposite 30 degrees, which means it's related to R times sine 30 degrees. This will be a common usage when we start doing physics on inclines. We know R is 4, sine of 30 is 1/2, so R parallel, the amount of the R vector parallel to the incline, must be 2. I said this is a common usage because a vector that's pointing the same direction as R is the acceleration vector, which we commonly call G. And so if you wanted to break G into its components, well, we have G parallel, and G parallel, again, is opposite the angle of 30 degrees. So G parallel is equal to G sine 30, or G sine of the incline. And this will be commonly used when we get to the physics of inclines and Newton's laws. Here we have vector A parallel, and vector A perpendicular. And made vector A and broken into its components, like you've seen in the lecture. But I can take this vector A and make into this component AX and AY. It's still vector A broken up into different components, a parallel, perpendicular, or an X and a Y. I still use Pythagoras' theorem, A squared equals A squared y plus AX squared plus AY squared is equal to A squared. A perpendicular squared plus A parallel squared is equal to A squared. A parallel plus A perpendicular in vector form. So I've taken A and I've broken it up into 2 different components. A parallel, I can call C and D. Or I can use the unit vector notation, I hat and J hat. I can pick a vector and break it up into components in any directions I choose, as long as my components, by definition, are perpendicular, whether parallel to an incline, horizontal to an x-plane, whatever I choose. Or in any particular direction, when I want to say it's the I hat direction, and a component parallel to the J hat direction. So here's AY in the J hat direction, here's AX in the J hat in the I hat direction. So this vector A has been broken up into components. An amount in the I hat direction of AX, and an amount in the J hat direction of AY, where AY is the amount, the magnitude of the component in the J hat direction. AX is the magnitude of the vector in the I hat direction. So the vector A is equal to the scalar amounts, the magnitudes of AX and AY in the directions of the unit vectors I hat and J hat. It's a more general notation rather than expressing things in parallel, perpendicular, and X and Y. In general, we have 2 parallel components, I hat and J hat. So let's say AX is equal to 3 and AY is equal to 2, for example. Those would be the scalar amounts. So I'd say AX plus AY, those are my vector components, equals the overall vector A. AX times I hat Vector amount of AX is 3 in the I-hat direction. The amount of the vector A in the j-hat direction is 2. It's 2 units in the j-hat direction, 3 units in the I-hat direction is the components of vector A. Now let's look at this story here. You've already seen this in the lecture, and it's one of your lecture quiz problems. You walk 50 meters north. Circle the information you need. You turn 60 degrees to your right. Walk another 40 meters. Then you turn again 30 degrees to your right and walk another 20 meters. How far? Net displacement. And what angle are you from where you originally started? It's looking for the displacement, how far, and the angle from your original starting location. After turning 60 degrees and 30 degrees, walking 50 north, then 40, and then 20. This is an example of vector addition. We have 3 displacements that we're going to add to create 3 vectors. Our first displacement, 50 meters north. Then we turn 60 degrees and 40 meters. 60 degrees. Then if you turn another 30 degrees after walking 40 meters, you've turned a total of 90 degrees. We walked 50 meters north. And we turned 60 degrees to walk 40 meters. After turning the 60 degrees to walk 40 meters, we turned another 30 degrees, which means we've turned a total of, through an angle of 90 degrees from our original angle. So now we have this final 20 meters after turning 30 degrees from our last turn or 90 degrees from our original turn. Let's call these 3 vectors A, B, and C. So vector A plus vector B plus vector C is equal to vector D. This does not mean A squared plus B squared equals C squared is equal to D squared. This is not true. This is not Pythagoras' theorem. Pythagoras' theorem is a right triangle. The 2 small sides add up to the hypotenuse. We have 3 vectors. 3 vectors are not making a right triangle. So we do not use this. How do we approach this then? How can we possibly figure out the overall displacement? D. How do we figure this out? Oh, this is still vector addition of 3 vectors. The magnitude of D relates to vector A plus B plus C. Its magnitudes and their directions. We can still solve this with vector addition, but we got to be careful. We break vector B into its components, make vector B the hypotenuse of a right triangle of components by and bx. Now by and bx are the components added to vector A and C, and we overall have D as the hypotenuse of the right triangle of vector A plus by, vector bx plus C. So A is entirely in the vertical, the y direction. There is no component AX. C is entirely in the x direction. There is no component CY. And B is broken up into BX and BY. So vector D is equal to dx, the displacement in the x direction, and the displacement in the y direction. The displacement in the x direction is bx and the vector C. The displacement in the y direction is vector by and the vector A. This accounts for our net displacement in components. Our net displacement dx in the x direction, our net displacement in the y direction. That adds up to our overall displacement. Now d squared is equal to dx squared plus dy squared. So if we know the value of dx and the value of dy, then we can find the value of the overall displacement. And we know it's bx plus c is equal to dx, by plus a is equal to dy. Find those components. Then we can find the value of dx, square that. Find the value of dy and square that. Well, dx is b sine 60. How did I get that? The amount of bx is opposite the angle of 60 degrees from where you turned. B was the amount that you walked, and bx is opposite that angle, so bx is equal to b sine 60 degrees. B is 40 meters. Sine of 60 is root 3 over 2. So we have root 20 root 3 meters. By is found similarly. By is b cosine theta. 40, 1/2 cosine 60 degrees is 1/2 equals 20 meters. Again, from previous videos and material, you should be familiar with cosine 60 degrees is 1/2. Sine 60 degrees is root 3 over 2. Now we know the value of bx and by, And we already know the values, the magnitudes of A and C, so we can quickly figure this out. Theta is equal to inverse tangent dx over dy. So what is theta? And what is d? You now have all the tools to solve this and submit your answer as a lecture question for lecture quiz 3. Again, the key was to find the overall displacement and angle, break the vectors into components so that we can add those components up using Pythagoras' theorem. The end.